सो बायो इनऑर्गेनिक केमिस्ट्री के पार्ट 10 में आज हम टॉपिक जो शुरू करेंगे वो है कोऑपरेटिव लिगेंड बाइंडिंग टू एलोस्टेरिक प्रोटीन्स। इसके पार्ट 1 को आपने पिछली क्लास में थोड़ा सा देखा था। आज पार्ट 2 देखेंगे। तो इसके अंदर 3 चीज़ें मेनली इम्पॉर्टेंट हैं। फर्स्ट जो हम देखेंगे बाइंडिंग साइट से रिलेटेड होगी, जैसे इस केस में आप देख रहे हैं 2 बाइंडिंग साइट्स हैं। फिर लिगेंड से रिलेटेड होगी और फिर इवैक्यूएशन होगा। तो इस फिगर को आप मैं थोड़ी देर बाद डिटेल में लूँगा। उससे पहले 1-2 चीज़ और देख लें। व्हेन यू से कोऑपरेटिव लिगेंड बाइंडिंग टू एलोस्टेरिक प्रोटीन्स, it sounds that cooperative conformational changes generally depends on variations in the structural stability of different parts of a protein. The binding sites of an allosteric protein typically consist of stable segments in proximity to relatively unstable segments, with the latter capable of frequent changes in conformation or intrinsic order. तो आप यहाँ से जब देखेंगे तो आप ये देखें, पहले थोड़ा सा इसको देख लें। नो लिगेंड, पिंक सेगमेंट्स आर फ्लेक्सिबल, फ्यू कन्फर्मेशंस फैसिलिटेट लिगेंड बाइंडिंग, ग्रीन सेगमेंट्स विच आर दिस वन आर स्टेबल इन द लो एफिनिटी स्टेट। तो बाइंडिंग साइट्स पिंक सेगमेंट एंड ग्रीन सेगमेंट. Pink segments, as you can say, these are flexible. Flexible means these are moving like a flippers from here to here. But on the contrary, the blue segments are fixed and green segments are stables with a low affinity. So there are 3 things which you can say: pink, flexible, as well as reactable. Blue, reactable but not flexible. Then this green one, on the contrary, blue, I beg to say pardon, blue is not reactive but is flexible. Green is completely stable. When a ligand binds the moving part of the protein's binding site may be stabilized in a particular conformation, affecting the conformation of adjacent polypeptide subunits. So here you can find ligand bound to one subunit, binding stabilizes a high affinity conformation of the flexible segment. Here we are showing this one in the green part, right? The rest of the polypeptide takes a higher affinity conformation, and the same conformation is stabilized in the other subunit through protein-protein interaction. So protein-protein interaction is equally important. So when we say the conformational changes that occurs as the ligand binds can convert the protein from low to high affinity site or affinity states, which is in form of reduced fit, the degree of cooperativity in ligand binding to an allosteric protein can be calculated as we have shown previously, and now again will show in the Hill equation. So you can find here the second ligand molecule bound to the second subunit, here one. This binding occurs with the higher affinity that binding on the first molecule, giving rise to a positive cooperativity. So this way you can understand the part. Now if I proceed, models for cooperativity or models for cooperative oxygen binding to hemoglobin. So here we will see क्या हम बताना चाह रहे हैं, मॉडल्स कौन कौन से हो सकते हैं। इसके अंदर 2 पार्ट्स हैं, हमने इसके अंदर लिए हैं। इसके अंदर पार्ट ए और पार्ट बी के अंदर, ऑल्दो मच इज नोन अबाउट द स्ट्रक्चर ऑफ द T and R states of hemoglobin. We have already discussed in the previous lecture relating the stability of the T states as well as R state. The mechanism by which this structural transition occurs on sequential ligand binding still is unsolved. Two principal models for cooperative binding of oxygen to hemoglobin and ligand binding to any allosteric protein are widely used to explain the structural transitions. Uh, so first, if you take the Moon, Wayman and Chenoweth's model, commonly also known as MWC, or it is also known as concerted model, all subunits of hemoglobin undergo the transition from one conformation to other simultaneously. So you can find there is transition from one conformation to other at the same time. So it's occurring simultaneously. The ligand can bind to either conformation but binds each with different affinity. Successive binding of ligand molecules to the low affinity conformation, which is more stable in the absence of ligand, makes the transition to the high affinity conformation more likely. So if we proceed, then we say that model cooperative oxygen binding to hemoglobin part second. So in the previous model, if you check, that is MWC model, there was the changes, and now in this one, this is proposed by the Koshland. Ligand binding can induce a change of conformation in an individual subunit. A conformational change in one subunit makes a similar change in an adjacent subunit, as well as the binding of a second ligand molecule more likely. There are more potential intermediate states in the sequential model than in the concerted model. The two models are not mutually exclusive. The concerted model may be viewed as the all or none limiting case of the sequential model. So this is respect to both the way, and as I explained in the previous one, we can explain the process at different pH in the form of the graph. So transport of proton and carbon dioxide by hemoglobin first. Hemoglobin binds to and transport about 40% of the total hydrogen ion concentration and 15 to 20% of the carbon dioxide formed in the peripheral tissues of the lungs and kidney. The remainder of the proton is absorbed by the plasma bicarbonate buffer systems. The remainder of the carbon dioxide is transported as dissolved bicarbonate and carbon dioxide. And this is important that the solubility of carbon dioxide in blood is increased by the carbonic anhydrase reaction. So that carbon dioxide reacts with water and produces the proton with the bicarbonate ion, which occurs in erythrocytes. The binding of proton and carbon dioxide to hemoglobin decreases the affinity of hemoglobin for oxygen, favoring the release of oxygen to the tissues where the concentrations of these components are relatively high. Conversely, in the capillaries of the lungs, as carbon dioxide is expected and the blood pH consequently rises, the affinity of hemoglobin for oxygen increases and the protein binds more oxygen for transport to the peripheral tissues. The effect of pH and carbon dioxide concentration on the binding and release of oxygen by hemoglobin is known as Bohr effect. So, as I told you earlier that there may be a full question on Bohr effect. The effect of pH on hemoglobin oxygen binding curves is represented here. As you can find, when you are having pH 7.2, the curve is this one. And as you increase the pH, the sigmoidal shape becomes the more sharper, and at 7.6 it is a unique one. So as it increases, the theta value partially increases for all these cases. So if you want to concentrate on the graphs, then you should understand that this is in between the partial pressure of oxygen in kilopascal at the value taken theta, but different pH values. So pH 7.2, 7.4, 7.6. Why we are taking? Because this is the most suitable blood pH. pH of the blood is in between 7.2 to 7.4 plus minus 2 changes. Yeah, and you should also know that what happens when the pH decreases below 7.2 and increases above 7.6. All these are the interesting features, and that can be correlated with the things.